Hey guys, it's Jazmine. So today we will be discussing chapter 18 titled Glass and Glazing. So to start, glass plays many roles and takes many forms in buildings. Glass can frame spectacular views, dissolve the boundary between inside and outside, or welcome winter sunlight to warm a room. But when used without care, it can also create issues such as glare, lack of privacy, cold surfaces in the winter, and overheated interiors in the summer. But glass, when skillfully used, contributes to efficient, comfortable, and joyful architecture. Thoughtlessly used, it can make a building unattractive, uneconomical, and uncomfortable to be in. So the chapter starts by talking about a little bit of the history of glass. So the origins of glass are a bit lost in prehistory. It was initially used for colored beads and small bottles. It first appeared in windows during Roman times. One of the largest known pieces of Roman glass is a cast sheet from a public bath in Pompeii. This was measured to be nearly 3 feet by 4 feet, which was a pretty significant size for its time. By the 10th century, the Venetian island of Murano became a major center for glassmaking, producing crown glass and cylinder glass for windows. These early processes both began with blowing a large glass sphere. In the crown glass process, a heated glass sphere was attached to an iron rod called a punty and spun rapidly. The centrifugal force opened the sphere into a large flat disc or crown, which was later cut into panes. A telltale mark of this method was the bullseye, the center point where the punty was removed. The cylinder glass process took a different approach. A molten sphere was swung back and forth on the ends of a blowpipe, stretching it into a cylinder. The ends were cut off, and the remaining tube was slit lengthwise, reheated, and flattened into a rectangular sheet of glass. Neither crown glass nor cylinder glass was optically perfect, making it unsuitable for fine mirrors desired by the 17th century nobility. To address this, plate glass was first produced in France in the late 1600s. This involved casting molten glass into frames, rolling it into sheets, and then grinding and polishing both sides to achieve near perfect quality. Though expensive, this advancement allowed for the production of larger, high-quality sheets. By the 19th century, mechanization made plate glass more affordable, enabling its widespread use in storefronts across Europe and America. Around the same time, cylinder glass production evolved, with cylinders of molten glass being drawn vertically, producing glass sheets up to 40 or 50 feet. This innovation made large-scale glazing products feasible, one of the most famous being the Crystal Palace in London, which was constructed in 1851, and this was glazed with a staggering 900,000 square feet of cylinder glass supported by a cast iron frame. In 1959, the Pilkington brothers in England developed float glass. This was a method that remains the global standard today. So in this process, a ribbon of molten glass is floated across a bath of molten tin, where it hardens before touching a solid surface. This technique produces sheets with perfectly parallel surfaces, high optical quality, and a nice finish. So virtually indistinguishable from plate glass, but far more economical, float glass quickly became the dominant production method. Float glass has been manufactured in North America since 1963 and is now accounting for nearly all domestic flat glass production. Flat glass, primarily used for architectural and automotive applications, is distinct from other types of glass such as those used in containers, reinforcing fibers, or optical communications. The terminology associated with glass has evolved over time. In construction, glazing refers both to the installation of glass in an opening and to the glass itself. The professional responsible for installing glass is called a glazer, and individual pieces of glass are often referred to as lights. So there are a few different types of glass. This includes float glass, tempered glass, laminated glass, and insulated glass. And then there are the different types of glazing. So that is single glazing, double glazing, and triple glazing, which my partners will go into. But glass has come a long way from just being a transparent barrier. Today we have low E coatings, which help reflect heat while still letting in the light. There's also smart glass. So this technology lets glass switch from clear to opaque instantly. This is good for privacy or reducing glare without having to use curtains. So yeah, of course glass isn't perfect. It's fragile, heavy, and requires precise handling, but it's not, or it's something that we've grown to use, and it's part of the architectural environment. And yeah, I'm gonna pass it on to Ella to talk a little bit more about glass.
Hello, guys. Today I will be talking about different types of glass. So, glass can be produced with an amazing range of physical properties and appearance. We have low iron glass that has greater optical clarity than ordinary annealed glass. Then we have anti reflective glass, which minimizes reflections that occur when light levels differ significantly on opposite sides of the glass. And it is used, for example, for glazing in showrooms, display areas, and sports stadiums. Then we have silk screen or digitally printed glass, which allows for the addition of complex graphics to both interior and exterior applications. Self-cleaning glass is coated with titanium oxide on its exterior surface, enabling sunlight to convert dirt, dust, and other organic particles on the glass to carbon dioxide and water. Glass that can change its optical properties is called chromogenic glass. Thermochromic glass becomes darker when it is warmed by the sun. Thermo, temperature. Photochromic glass becomes darker when exposed to bright light. Photo, light. And then both types are potentially useful as passive devices to reduce cooling loads in buildings. Electrochromic glass changes its transparency in response to the passage of electric current. Also called switchable glass, it can be actively controlled by building occupants or automated systems in response to changing requirements. For control of solar heat gain, daylighting, or occupant privacy. So now we have chemically strengthened glass, which is produced by an ion exchange that takes place when annealed glass is immersed in a molten salt bath. This process results in a pre-stress in the glass, similar to that which occurs with heat treating. However, because the temperatures involved are lower, the chemical strengthening occurs without causing optical distortions. Mirror glass has a thin reflective silver-based coating on its backside. To prevent corrosion of the silver and provide additional protection, a thin layer of copper is applied over the silver and a backing paint is applied over the copper. Pattern glass, which is hard glass rolled into sheets with different surface patterns and textures, is used where light transmission is desired, but vision must be obscure for privacy. Glass manufactured with a high percentage of lead oxide can be used as a radiation shielding glass. Photovoltaic glass is coated with a thin film of amorphous silicon that generates electricity from sunlight and then can help reduce a building's electricity consumption. The traditional stained glass and the contemporary colored glass, formulated with ingredients that alter the color of the glass, can be used in a wide range of artistic and architectural applications. Glass may be blown, cast, fused, and colored to produce an infinite variety of types of art glass that are used for decorative and sculptural purposes. Mm,
Hello, my name is Chris, and I'll be talking about anything regarding glazing and the glass and how that happens. So first is plastic glazing. The two most common plastic glazing materials are acrylic and polycarbonate. Both offer good clarity and weather resistance. Both are softer, more easily scratched, and more expensive than ordinary float glass, and both have high coefficients of thermal expansion, which cause them to expand and contract with temperature changes more than glass. Acrylic glazing is 2 to 3 times more impact resistance than annealed glass of the same thickness. Polycarbonate sheets have even greater impact resistance and can be formulated by resistance to fire. Acrylic and polycarbonate sheets can be manufactured in a variety of colors and with varying degrees of transparency. They are easily machined, and as thermoplastics can be heat formed, such as dome skylights, and low E coatings can be applied to acrylic sheets to improve the thermal properties of the glazing. Polycarbonate sheets can be manufactured in a double-walled configuration called a cellular polycarbonate glazing, creating hollow panels that can be about a fourth of an inch to 1.5 of an inch. And with enhanced stiffness and thermal performance, these materials can also meet safety requirements for glazing used in areas subject to human impact. Glass fiber reinforced polyester glazing is durable and long-lasting and can be formulated with varying degrees of translucency and resistance to fire. Fiberglass sheets are frequently applied as a facing material over lightweight aluminum frames to make a translucent composite panels with higher thermal efficiencies. In corrugated form, fiberglass sheets are used as a utilitarian translucent roofing material, and with this and ethylene says your ethylene tetrafluoroethylene or ETFE is a translucent thin extruded plastic sheet material chemically similar to Teflon, and it transmits about 85 to 95% of visible light and is lightweight, strong, long-lasting, and it is also recyclable. It's lightweight and is approximately 1% that of glass and results in lighter and less costly supporting structures than required with glass. The material can be stretched between a surrounding frame or supported with cable network. Single-ply membranes have roughly the same insulating value as a single sheet of glass. Air-inflated pillows made of 2 or more plies achieve higher thermal efficiencies. Such multiply systems also require a network of inflation tubes connected to pumps to maintain pressure within the pillows. The material itself can be printed, tinted, or manipulated in other ways to adjust its light transmission and solar heat gain properties. And that would be plastic glass. And next one would be glazing small lights, and how that is done is the glass is set in glazing compound or caulk and secured in place with a wood stop. The stop is fastened to the window sash with fine finish nails or screws. Traditional glazing compounds are made from mineral oils and organic filler. They adhere well to glass, remain sufficiently elastic to accommodate small movements in the glass, and when painted, provide good weather resistance. Alternatively, low or medium range gunnable sealants can be used. In a double insulated glass unit is factory glaze into a wood sash. Resilient setting pads provide support and cushion the glass edges. On the exterior side, silicone sealant acts as the primary weather seal and as adhesive to hold the glass in place. A thinner bed of sealant cushions the glass on the interior side, and a wood stop mechanically attached or glued in place secures the glass within the frame. Other frame materials may also be used, such as vinyl, aluminum, or fiberglass. Glazing systems such as these are suitable for door and window systems not subject to large wind forces or large movements due to thermal expansion and contraction within the glass or frame. And that's how glazing small lights would be. Next would be glazing large lights. So glazing for larger glass units must secure the glass against larger wind forces, resist the passage of water and air under more severe exposures, and accommodate larger differential movements between the glass and the frame. So that means that the glass must securely supported yet gently cushioned where it is held by the frame. The glass and frame must be able to expand and contract independently with changes in temperature. The edges of the glass must be free to rotate slightly as the glass deflects under wind loads. Contact between glass edges and the frame must be avoided to prevent damage to the glass. In general, dry glazing components such as synthetic rubber gaskets are quick and easy to install, consistent in profile, and relatively free-form variations in workmanship during the installation. However, the lack of adhesion between glass and frame may permit the glass to shift position within the glazing pocket. Wet glazing components such as silicone sealants adhere glass to frame and form more complete air and watertight seals when installed with adequate care. Solid glazing tapes such as butyl or polysulfide also adhere glass to frame and can maintain consistent controlled joint depths. And there's also what is called advanced glazing systems. And what that is that in butt joint glazing, the head and sill of the glass sheets are captured conventionally in metal frames, but vertical mullions are eliminated entirely with only silicone seals between glass joints. Butt joint glazing produces windows with strong, unbroken horizontal bands of glass, where the appearance of flush glazing is important from the exterior, but vertical glass edges require support. These edges can be adhered to an interior mullion and structural silicone sealant. In structural glazing, glass units are not mechanically captured at all, but rather held in place solely with structural glazing adhesive. Both structural silicone sealant and acrylic foam structural glazing tape are used for this purpose. These adhesives are strong and permanent enough to reliably hold the glass while resistant wind pressures, thermal stresses, and other forces that act on the glass over the life of the window system. Usually, the application of the adhesive occurs in a factory under controlled conditions where the quality of the bond can be assured. In point-supported glazing, glass units are held only at their corners, and both horizontal and vertical units are flush glazed with silicone seals. The hardware used in the system provides support against gravity and lateral forces while non-imparting unwanted bending or torsional stresses into the glass. And glass and energy go hand in hand. So, glass is a two-way pipeline for the flow of both, conducted and radiated heat, even when doubled or tripled. Glass conducts heat rapidly into or out of a building. It can also admit large amounts of solar heat into a building. In residential buildings, the conduction of heat through glass should be minimized in the extremely hot or cold seasons of the year. Double glazing, low E coatings, low conductivity gas fills, and snug curtains or shutters are desirable features for a residential window or windows. Warming sunlight is welcome in winter, but undesirable in the summer, which leads to conscious designer or orient major windows toward the south, with overhangs or sunshades above to protect them against the high summer sun. Large east or west windows can cause overheating in summer and should be avoided unless they are shaded by nearby trees or other features. But in larger residential buildings, heat generated within the building by lights, people, and equipment is often sufficient or more than enough to maintain comfort. But throughout much of the year, for this reason, controlling unwanted heat gain is often an important consideration for window systems in larger buildings. Tinted and mirrored and low E-coated glass units with low solar heat gain coefficients are common choices. East and west windows can be especially problematic as they contribute strongly to summertime overheating and are difficult to shade. Shades or blinds inside the glass are helpful in eliminating the glare, but they do less to keep out the heat because once sunlight strikes them, its heat is already inside the building and little of it will escape. Glass in buildings also plays an essential role in daylighting strategies. Natural daylight improves occupant well-being and efficiency. It also saves energy by reducing the consumption of electricity for artificial lighting and reducing cooling loads on the building or conditioning system. And that is the end of chapter 18. Thank you.